weights on all the variables. Okay? Unless you want to do unequal weights. Okay? If you want to do unequal weights on the variables, then you can use and use still using Euclidean distance. You can use goal distance. So in that case, you need to use the DAISY function, not DIST, the dist function. So we run that.
I'm sorry, you said the Lacy function?
DAISY, D-A-I-S-Y, from cluster.
Okay.
Okay.
For case study 5. Equal weights.
Okay, so there's basically no difference using DAISY function or this function if you put equal weights on variable. Okay, they in the original paper Goal actually showed that this Goal's distance is equivalent to Euclidean distance when all variables are numerical. Of course, that's under the equal weights situation. And of course, R has this DAISY function under cluster. So DAISY, right? DAISY. Okay. DAISY function has the choice of goal distance. Even if you apply to numerical variables, but you want to put unequal weights of variables, you can still use that. So remember we talked about that. Goal distance. Okay, so maybe. So here, for the DAISY distance, or for the goal distance, okay, applying DAISY function. So you look at that. The default distance matrix is Euclidean matrix. As you can see that it's Euclidean. Manhattan is second choice, and the goal distance. Okay. Now when you choose goal distance without changing the weight basis, that's supposed to be the same when you have all numerical variables. But if you change the weight to be unequal weights placed on the variables, then you can use goal distance apply on the Euclidean distance. You can still run random forest to judge the variable importance, right? Isn't it? Okay. For the scale of variables, okay. And of course, in caret package, it also allows you to first eliminate those near zero or near constant variables, right? Isn't it? Okay, we'll talk about that, right? So originally, how many variables do you have? 38, right? Originally.
How can we run importance without target variable?
Well, random forest allow you to do that even with unsupervised case, right? You can run variable importance with unsupervised case. Look at the help documentation of random forest. Yeah. And what else? Okay. Caret first look at these predictors, right? And then you can eliminate predictors that are near constant, right? Okay. So maybe you can eliminate few variables right away. Okay. So that's one thing you can look at in the supervised learning. And for K-mean clustering, unfortunately, in the default, and actually K-mean does not install other distance measure. It's only the Euclidean distance is applicable. So unfortunately, you can only run the Euclidean distance on the scale data. Of course, you need to scale. You need to scale the data because the variables are not compatible, right? So the scaling of the data is really important. Okay? So use a scale function to scale your data. Okay. Anyway. So for K-mean clustering, you don't need to use other major other than the metrics other than Euclidean distance. Just use Euclidean distance. You might want to try PEM as well. To have this partition around the door, so maybe may want to try that. Try that to see if that works. This is PAM. Matrix is Euclidean. Do we have choice in the PAM? I forgot about that. Yeah, PAM around you to do Manhattan distance. So maybe that's where you can. Right? This is a partition around the doors. But K-mean clusters, according to the installation, you're only allowed to use the Euclidean distance. Any other partition? I guess that's the only one you have in the cluster package. In a sense, PAM is sort of equivalent, or not exactly, of course, equivalent to K-mean cluster. In K-mean cluster, you cluster around the centroids, but PAM cluster around the matroid. But PAM allows you to specify Manhattan distance as well, so maybe you can try this. You say you already have too many different models, right? Okay. Actually, you use a different method. Use like Diana, or use like this Agnes. And you can see that there's not similarities. Well, at least that there are a few observations we stand out consistent. You might want to exclude those, maybe a couple of observations, okay, from the rest. Just exclude them. Then we plot your dendrograms. Okay, here the next subject we talk about is so-called self-organizing maps. This method is closely tied to a method called learning vector quantization. I should say that it's LVQ. Okay. Quantization. So-called LVQ. Actually, both are proposed by the same author, Cohen. This self-organizing maps. In a sense, the idea is quite similar to principal components analysis, in a sense. Okay? Except that principal components analysis in many situations requires not just the components. Maybe you need 3 or 4 different components. So really hard to visualize in like a 2-dimensional space in some situations. Okay? Learning vector quantization is from this vector quantization idea, which is quite a classical method in signal processing, okay? Where basically the idea when you want to send a signal to a distance, okay? It's kind of equivalent to sending the so-called coput. Okay? They send the coput first, and then send the indices. You don't have to send the code directly to them. Just send indices indicating in that coput on which page, on which line, to find that, something like that. Okay? So, and self-organizing map actually is kind of combining the idea of this learning vector quantization. But of course, in the process, this self-organizing map using this idea, this learning vector quantization. So you can see that this process is like a training procedure. You start with some very initial states, and then gradually modify the result, and finally reach the clusters. Okay. So that's a self-organizing map. Well, this is meant to be only introduction, and I'm trying to get into all the detail. Okay. This is a constrained versions of k-mean clustering in a sense, okay, and it's considered as a crude variance of this multi-dimensional scaling. There's a difference between this MDS, okay, multi-dimensional scaling, and this so-called self-organizing map. Okay. Basically, I kind of just refer you to read this articles from this R News. It's right here. Okay. This is a. Let me increase the size so you can see better. Not R News. This is Journal of Statistical Software. And this is freely available online, so you can check this. Check about this self and super organizing maps in R, this column package. So actually that means that you need to install the column package. Okay, if you install this column package, this is also included in the document directory, so you can see that there. Okay. Otherwise, you can also go online and look for this. Okay. So basically, in principle, multi-dimensional scale, in a sense, try to look at the largest distance, in a sense. Okay? So try to look at, in a sense, it's a low dimensional estimate of this high dimensional distance. So it's in a sense the multi-dimensional scaling try to reduce them down to few dimensions and very often it's a two-dimensional case. So it's a two-dimensional representation of distance matrix of this high-dimensional data. Let's say you have data start with like our example 38 of the 38 variables. This is really high dimension. Okay. And multi-dimensional scaling is like this two-dimensional representation of the distance matrix. And usually the object with the largest distance will be more truly estimated by using multi-dimensional scaling. Okay. But the self-organizing map, on the other hand, is also very similar to that to this multi-dimensional scaling, except that they only keep the topology, means that the neighborhood, okay, only keep the neighborhood. If in high dimension two objects are similar, then you map it to this low dimension, they are still quite similar. Okay, that doesn't mean they keep the distance. Right? So if objects are more similar in high dimension, they tend to make it even more similar in the low dimensional case. So keep this only the neighborhood situation. Okay. And actually, there's some similarity of this method here. This learning vector quantization is sort of nonlinear version of principal component analysis. You can call it that way. Okay. So usually, principal component analysis is actually trying to find for data clouds like this. Okay, we try to find a principal axis, right? That this principal axis account for the majority of the variation, okay? And another, the second principal component, that's a directions that is perpendicular to this direction. Okay, learning vector quantization, in a sense, okay, sort of similar to that, except it's a nonlinear context. Okay, where instead of having like view data clouds having like like very regular shape. Your data plot could be very irregular shape. I'm not sure if I can make this right. Okay. So basically, this learning vector is trying to find a nonlinear direction that accounts for the majority of this variability, rather than look at a straight line. Okay. So in a sense, there's now similarity. And the self-organizing map use this. Okay, use the idea of this learning vector quantization map to only 2 dimensions. Okay. So it's a low-dimensional representation of the multi-dimensional data. Okay. Discretize representation of the input space, of training space, samples. Okay. The other thing that is quite different of this self-organizing map and learning vector quantization comparing to the principal component is that principal component is sort of mapped to a continuous space. It's only have a rotation, still continuous space. Okay. And learning vector quantization mapped to a discrete space. Okay. So mapped to only quite a few representation of the input space. Okay. So basically, this is also known as this is constraint topological map. Okay. The idea is that maybe this idea of self-organizing map is better. Okay, interpret this way. Basically, the idea is try to take all the objects within your data set and map into discrete sets of units, okay, which he called Cobook. Okay. One way of this Cobook is to just arrange the Cobooks in this rectangular array. Okay. So here you have this 1, 2, 3, 4, 5, 6. So here this is rectangular grids of the Cobook. And how many do we have? 4 to 5, right? This is 4 by 5 grid. Okay. And the idea of this column map, when the data present an object, let's say this object is presented here, okay, is trying to match this with this Cobook with the shortest distance. Which one is the shortest? Maybe this one, right? Okay. So here this object, when it was presented, it find that this object is nearest to this point, and it takes like winner take all stratus, meaning that this is going to be absorbed to that. Okay, not exactly. Right? The idea is that you gradually modify your Cobook. Okay? So the next step will be when this is found that this object was found nearest this one. Okay, it's kind of sort of try to migrate to all this, not exactly completely merge this two with the object, but they use some kind of learning, like a learning scale. Okay, so usually you probably migrate to, I think they suggest alpha with 0.05. So take a small step toward that. Okay, 0.05. So means that will be 5% closer to that point, right? Isn't it? Okay. So here this would be modified to maybe use this color. Okay. So probably roughly, let's say, suppose this is about 5%. Between this point and this point, this is about 5% between these 2 points. So 5% closer to that. So the first step would be something like this. Okay. So here the Cobook will be modified to this. Okay. Something like that. The idea is that finally you try to find all the objects in your data set and try to place into this grid. Okay. And then of course in some cases some discrete point will contain a large number of objects in there, and that actually form an idea of the clustering. Okay. So next step will be this. So here this Cobook, this will be modified to this. Okay. And next one, suppose another object is presented. Okay. This is not a very good representation of that. Okay. Suppose next one is this. Okay, somewhere here. and probably closest to this one. Okay, so next one, this will be drawn to that. Okay, and hopefully my drawing is okay. Right? Okay, so here this one will be drawn to that. Okay, to that object. Okay, so and that means this object will be pressed into that grid. Okay, so the grid point is gradually merged. This corpus is gradually merged with your data set, the distribution of data set. And finally, probably the final result of this data set will be something like this. Okay. I hope I can draw this. So exactly, okay. It's not very good drawing, right? Okay. So finally, you probably have some grid point like this. Okay. I hope this is not really good drawing. Looks fine, right? Isn't it? So you can sort of having this topology here, okay? Okay. So actually, this means that in high dimension, if 2 points are close to each other, and this low dimensional representation, they are still close to each other. Okay? They are more likely to be clustered within, to be grouped into the same cluster. Okay? That's a very, very basic idea. This is so-called self-organizing that. Okay? And the small step. So this means you need some kind of training of this result. Okay, it takes some maybe 1,000 iterations to do that, and usually the computation is really fast. Okay? So you adopt this winner-take-all strategy on that. Okay, just find the nearest one. So observations are processed one at a time. A batch version was later proposed. Actually, there's another package. It's called batch SOM. Okay. Batch SOM is just a different way. Okay. Here, this is the data from the package class CLASS. Okay, so here. I don't know why this is in this package. This looks like classification, isn't it? Okay. Class package has this data set and also have this cell organizing map function. Okay. And cohort package is sort of a small refinements of that of this class package. Okay. In this package class, we have this data set Krebs data. Okay. It has measurements on the 50 Krebs. It's some kind of morpho. I'm not sure what that is. You want to know about this? This morphological measurements. And 50 Krebs, each of 2 color forms, okay, either blue or orange, in both sexes here of this Krebs. Okay. The 5 measurements on this is frontal lobe size, and all measured in millimeters. Okay? And this RW, real width, CL, CW, PD. Okay? It was a different 5 measurements. They are all numerical measurements in this data set. And here, this is the corpus representations of these 5 measurements. There are different ways of plotting this. Here, this is so-called star symbol. Okay? Star symbol, in this case, we have 5 variables, right, isn't it? Okay. The 5 variables are scaled. The usual way of scaling this is to scale toward the range of that. Okay, so this arm represents 1 variable. Okay, so this is another one. In a sense, this is the measurement for that same variable from the other pair, right? This data set. Okay. This sounds interesting, right? Star symbol, okay. And we have 5 measurements. So we have 1, 2, 3, 4, 5. Okay. Well, in a sense, this is graphical representation of this 5-dimensional data using the star symbol. where each variable was a scale from 0 to 1. Okay, by you can take your measurement minus minimum divided by maximum minus minimum, right? That would scale from 0 to 1. Okay. So you can see that for this one, we have all the measurements are very small, yeah, compared to others.
What's that dot? Is that the perfect crab, or is that the
Not this
smallest
very
crab?
small crab, I think, compared to all others.
Could that be a missing value that would cause that? Like, these are like Chernoff faces, right?
It's probably not a missing value. It could be a missing value, maybe.
Okay.
More likely missing value. Otherwise, you should have some.
And then these diamonds.
Well, of course, if this crabs has all the measurement as with the smallest measurements in all dimensions, of course, you see a dot. That could be a case. Could be the case.
And then these are just like Chernoff faces, right?
Huh?
The faces. These are like the Chernoff faces.
Well, this is not Chernoff faces. This is a star symbol. Okay. Well, there are
It's
different ways
similar.
of representing Montevideo.
But is it similar to that?
Similar to that. Actually, Chernoff, that's not Chernoff. Chernoff faces is more. I guess probably when you ask, I have to let everybody knows. If you never heard about this Chernoff faces, Chernoff faces this is graphical representation of multivariate data using the facial characteristics. Okay. So you probably have a data set represented like this, some represented by this.
Right.
Maybe here, right? Okay. And then others probably represent with that with very long head and a short nose, okay, and then anyway. Okay. And that's called Chernoff faces. But it's Chernoff face is too subjective.
Okay.
Yeah. In a way, this is more objective way of presenting the multivariate. In this case, we have 5 dimensions only. So here, these are there are 50 crabs, right? Here we have this graphical representation of these 50 crabs here. 1, 2, 3, 4, 5, 6. We have 50 here. Only 48. But not all of them, huh? So I probably should mention this is not the representation of all the crabs. This is like the cohorts, okay? And finally, the final result when you do the cell organizing map, this is like the final clustering. So you can see that within this grid there are many observations here, right? And so actually, nature you can see there's a natural cluster here, right? Maybe you can also consider some few adjacent cluster as to be near them. Okay. So you see at least 1, 2, 3, 4, 5 to maybe 5 to 6 different clusters. But there are some sort of very isolated observations, very different than others in the cohort. You can see that. Okay. Now here I use 2 different colors for this, 2 different. We call this probably the same species but with different colors. And both sexes use uppercase, lowercase represent a different. I think I use uppercase for males and lowercase for female. I forgot what I did there. Okay. This is outcome from running a self-organizing map. Okay. And there are some other considerations you can finally, based on this. The final result, and you can cluster them into several different clusters. Okay. The algorithm that you can see in this package class and also in a component package that usually there are 2 different types of cohorts. One is this rectangular grid, okay, like the one you see here. The other one is this hexagonal types of grid. Okay, so basically you're looking at the grid points. Like, I'm not really good at drawing this, right? This is like more like hexagonal, right? Okay, and so on. Okay, so here this hexagonal grid, of course, it would be easier to represent with just a circle. Okay, so there's a different way of representing this. Okay, this grid. So you start with a large number of clusters and arrange in grids. Okay. For example, in this case, I arranged this is how many grids do we have? We have 1, 2, 3, 4, 4 by 5. There are 20 grids, right? So you sort of start with about 20 clusters. By finally, when you look at the final result, meaning that you don't need that many clusters. You reduce to only quite a few clusters with this result. Okay. And our package class, the default grid is 8 by 6 rectangular grid with 8 horizontally and 6 vertically. Okay. And you can also choose hexagonal grids as well. Okay, that's another option. 8 by 6 hex bins. Okay, so it's another choice. Okay. And the representative space is the centroid, okay, in K-means, and where it's used by as spatially correlated. Okay. Cohen use different terminology on that. Either they are representatives or the terms used in K-means would be the centroids, okay, and used by Cohen to be the weight. They are sort of equivalent. Okay. And representatives at nearby points on the grid are more similar than those which are widely separated. So you can see, look at the final result. Okay. So more likely, I probably would cluster this. I probably could put this in the same cluster, right? For example, okay. And maybe this is another cluster there, another cluster. So it looks like there are 1, maybe 2, 3, 4 or 5, could be 4 or 5 clusters. Because these two clusters are nearby, so you may consider to merge them into one single cluster. And of course, this is not exact method. This is still a random method. Okay? This is a statistical method. Okay? This representative is 1. Okay, then. And this representative is modified, it's updated. So Voyager migrate into this data set. So they finally will map within this data set. I think it was a recommended, like the alpha in the training process. I think Cohen suggests alpha to start with 0.05. And gradually decrease linearly to 0.01. I think that's what he recommended. Maybe here there's a study about what is the best strategy to change this alpha. Okay, so here basically this is the idea of SOM. I saw a different recommendation. I saw from one place they recommend from 0.05 down to 0.01. Okay. Here this is another recommendation. Okay. Maybe for particular study they define this out. Okay. Alpha declines linearly from 1 down to 0.04 over 1,000 objects. Okay. So basically you create from alpha equal 1 to 0.04 equal space this result. Okay. Not necessarily equal space, right? It's only to decrease the alpha linearly over the 1,000 object and declines linearly to 0 over the second 1,000. Okay. I saw that another recommendation, Cohen and Sol suggests like using 0.05 times 0.0. And the definition label is a grid point I within distance r of j, where r declines linearly from 6 down to 1 over the first 1,000. I think in the covenant recommendation, usually you want to, at the very beginning, you want to consider about 2/3 of the entire data set as its neighbor and gradually decrease. That's what he recommended. Use like 67% to start with. Actually, that's implemented in the SOM and in covenant packages. You can see that. And class package comes with a standard distribution, so don't need to install any like additional package. It's in the standard distribution of that. Okay. I was surprised to find there are not too many functions in here. Where you can see this SOM right here, capital S, they're all capital. Okay. And SOM grid is to define the grid points either rectangular or hexabins, okay, like this, okay. And you can still see this this learning vector quantization. Okay. Covenant come out with like 4 different versions, 3 to 4 different versions of this learning vector quantization. Okay. Doesn't mean that you the one is always better than the other. It kind of suggests use a combination of maybe the second and third one, right? Which we're not getting into the detail. So you can see a lot of this is dependent on that. It's LVQ, this 1, 2, 3, 4, 5, 6, so related to this linear vector quantization. And SOM, and here and SOM grid and batch SOM here. This is one that we mentioned. This is a batch run of that, rather than presenting one observation at a time. Okay. Call and come up an algorithm that can deal with this, with a batch of objects to present at a time to the map. Okay, to revise it. I think the idea of this batch form is try to make it the algorithm run faster. In this package, you also see this k nearest neighbors as well. Okay, so and data queries come from a mesh package rather than from that. Okay. So here we need to get this data set. And as was suggested in that help documentation of data, you can use a help. How about this help? They're supposed to have help. Oh, okay, when you want to, okay, so you can do that. Okay. You need to specify package otherwise, because we didn't load the package. Unless you load the package, you can just do the help. In this help documentation and other, there's actually a natural logarithm was suggested to convert this measurement. Okay. So it talks about this. SP is species, okay, either blue or orange, and sex and index. Basically, just indexing this 50 crabs. That's all. Okay. And the rest are this quantity measurements. Okay. And was suggested. Okay, natural logarithm on this numerical measurements was recommended on that. Okay. So actually, we do that. Here, from column 4 to 8, okay, we use the natural logarithm of this result. guess I don't have to do this way. There's another way to build up this, but I would just want to use this without. It can use the interaction function to interact two vectors to get all possible combinations. But I do this directly anyway. Okay. We assign this vector. So here this blue crab, this male blue crab and the female blue crab, and the orange male orange, and this is a female orange. Okay, so here this vectors. Okay. And here this is training function. S1 is training function of this cell organizing map. Okay. Cell organizing map will log grabs data and some grid. Okay. Topology used is rectangular. This is default. Okay. So actually in this case you don't need to specify that. Okay. It's rectangular grid. Okay. And of course, some grid is topology allow you to do partial matchings of this. I think use R will be enough. Okay. And H for hexapin. Okay. Now here we sort of using this learning rates, okay, with alpha. And look at the health documentation. Alpha provided as a list. You actually sort of train this twice. Okay, first we start with the learning rate starting from 0.05 and decreasing to 0. Then this is so it's 10,000. I think I use a 10,000 observation. So 10,000 different values of alpha decreasing from 0.05 down to 0. Okay, and next, okay, we'll start with 0.02 and down to 0. Okay, this is even more, right? Okay, it's 100,000 such observation. And define a neighboring radius by this. And in this package, the plot is the star symbol as the default. So let's look at this result. Here, this is more like. So here we have 1, 2, 3, 4, 5, 6, 7, 8. Remember, this is default. Okay. In the default implementation, there are 8 grid points horizontally and 6 grid points vertically. And now here, this is a star symbol representation of the centroids. I should make it more clear. Okay. So 8 times 6, 48, right? We have 50 crabs only. So most likely when you cross the result, you will find empty grids later on. Okay. So we start with this many grid points on that. Okay. So if you plot this S on, this is in star symbol, that will be the result of that. Okay. And let's look at that's what's suggested in the class package. You can also use the one nearest neighbor, okay, to come up with this hexapin and use that in the result. Okay. And this one, you say type equal null, basically set up the grid, not to plot anything, so you see empty plot there. Okay, this is for plotting. Okay. And at the grid points, we finally plot this result. This is the circle representation of original grids. So you have in the rectangular grids, you have 8 grid points horizontally and 6 grid points vertically. Total 48 grids. Okay. doesn't produce the data. It's only the original method, original code book. And you can define the 4 colors we use important symbols. Okay, I choose these colors. Okay. Somewhat semi-transparent colors so we can see it overlap better in this result. Okay. Get object label. Okay. And here this is the object that represent that sort of press into that. Actually, I did some kind of jitter, means I add random amounts of this object within that. Otherwise, everything will be superimposed in the center. Right? So I take the center of this grid and sort of add some random amounts to that, and it's done in this text command here. Okay? So here perhaps SOM the grid points are being plus some random amounts, small random amounts to that. Okay? Actually, this package class it's already very steady, very stable packages. Okay? And column packages, in a sense, try to enhance this package, and actually it's still quite a stable package as well. You can see the column package later. Let's look at this one. Okay? Let's see an arrow there. Oh, it sort of jump. This is a star representation of the data. Remember, there are how many numeric variables we have in forensic? There are 9 numeric variables, right? Isn't it? So you can see which star symbol we better see all the 9 variables here. So you can see 9 variables in this one. Okay. The 1, 2, 3, 4, 5, 6, 7, 8, 9. So each arm sort of represent a variable, scale down between 0 and 1. Okay? So. And now here we use a hexabin grid, so that's why you can kind of, okay, they kind of sort of put it in this hexabin location, right? Like the one, okay, like this location. Okay? The offset, okay, between rows. Okay? And this is like this the code book. This is the representation of original code book in this form. Okay? It's an hexagon there. Okay? Gives a circles function to that. But remember this example. Our original variable, our original data set is for classification, for supervised learning. You can also put SOM, this self-organizing map, in use in the supervised learning as well. By adding, Collins suggests that you also need to add the information of this dependent variable response into the consideration when you train the SOM. Okay? So then that allows you to do a classification as well. Okay? Now let's look at the result in this cluster here. You can see how many clusters we should have here.
One big one.
Well, according to the data, we are supposed to have 6 clusters, right? There are 6 different types, right? Can you see that? Of course, you also have to look at the distances. There are ways to plot distances, corners. In the corner package, you probably have better view of this result rather than using this just a class package. And see, I only use the first sort of one of the letters represent each class. So it's F for that, N for this, and B for that, and so on. Okay. Of course, if you use a cell organizing map, I think you're going to misclassify a lot because you can see all these different like different class types sort of located near each other, right? If you look at this result. Okay, so you still see a lot of misclassification, actually. Okay. And of course, again, if you form a cluster, the winner will take all. Okay. If you form like, for example, if you take this as one cluster, okay, most likely you cluster as from this one edge, right? Okay. So here this cluster is supposed to be like for edge type because we have more of the edge for what? That is for edge for vehicle, right? Edge for headlamp. Okay. Actually, although it's recommended, like, well, you can use SOM for classification, but it doesn't do a very good job in this result. Okay. I have another script files, but I didn't put it online yet. Okay. Basically, you can also look at these column packages and see the result. Okay, of that. Okay. And this is a column package, so this means that you have to install this package. You do not have that by default. Okay, so this has to be installed. Okay. For some reason, I tried to update this to the current version I'm running. It failed, but it's still okay. I still can run this result. Because every time I load this, it always gives me a warning message. And I was trying to revise this. I was trying to update this. Okay. Every time fail. Okay. I don't know why. I probably need to review this package. This package uses this particular data set, okay, in their favor to try to explain this self-organizing map. Okay. It's built data frame from column package. Okay. Again, this is a data set with all numerical measurements on the columns. All columns are numerical. Okay. There's no non-numerical data. I'm not sure whether this algorithm will work with non-numerical data, like doing some kind of goal distance. See, through goal distance, you can define goal distance. You can also define similarities through that. Okay? Not sure if they can do that. Okay? So here, suppose we train this data set. Okay? With this self-organizing map. Okay? I use a 5x5 rectangular grid. Here, look at this result. Okay? This is some grid. Okay? Column just build in some other arguments as well to train more. This is hard to remember what this stands for. Arguments. Recall what this is. See, look at this. The alpha is between 0.05 down to 0.01 in. Oh, maybe this is number of. I think that's probably number of alphas used. Okay? I have to look at that. Okay? But it's kind of decreased from 0.05 to 0.01 linearly. That's what they use. Okay? And radius means that the very beginning, the neighbor definition is defined by this. Okay. Well, at first you look at this is very hard. This is something that is related to the R function. This is not considered good features in R because this maintenance is not so easy. This NHBR DISD, this is some object, or this is some object created within this function. I use something called sort of lazy evaluation. This object appear first, followed by this radius, and then use radius, and then define a neighborhood distance as from between like 0.67. Remember earlier I mentioned that at first it considered about 2/3 of all observation as the neighbor of any object. Okay? So that's what it is. So as you can see, the radius from like from 0.67 to negative 0.67, right? So including this radius. Okay? And it also has another argument here. This how do you pronounce this? This toroidal. Toroidal. Meaning that, well, this is kind of a twist from the original idea of this SOM. Original idea, like, for example, you have this rectangular grid, okay? The two edges are separate, okay? Toroidal means that you can walk this, this neighborhood. So in the sense that the two opposite edges will be connected, okay? That's what that is, okay? By default, it's false, okay? If you without that true, it would be very different. I guess that's only probably useful for even higher dimensional case. You can use that, okay? Okay. So here we train this data set and then we plot the code. Well, this is only just well, what should I say? How should I call it? This is like sort of even sort of. I shouldn't say this is better representation of the star symbols, but this is still a star symbol in a sense, right? I use a color to represent different variables rather than using the arms here. Okay, like this one, the first one. This is like I think this is alcohol contents. Okay. On this direction, right? So that's the first one, okay? And the second one is, what is metallic exit anyway? I don't know anything about wine, so maybe I shouldn't say anything. This is a metallic exit. This represent, which one will just show better? Right, this one, right? Second variable right here, right? Okay. And third variable is ash. Did they push ash in there? So maybe this is so ash is like third directions and so on. So actually that's how here the legend here basically tell you that this how many measurements we have? 1, 2, 3, 4, 1, 2, 3, 4, 5. Okay, we have 13 measurements, right? These are the 13 variables. Okay. In case of your this water treatment data set, you have 38 variables. It's going to have 38 dimensions on that. Okay? That's a lot. Okay, but of course that maybe you want to run the variable importance first. Okay, try to reduce number of variables and see. Okay, come out. You can also use a cell organizer there. I'm not saying you should do that, but okay, you can try that. Okay. So here Remember we did this in 5 by 5 grids, right? So here we have 1, 2, 3, 4, 5, right? So we have 5 grids horizontally and 5 grid points vertically. And then here these are the centroids of that for each cluster in this self-organizing map. Okay. Where was that? What was this? Here I tried another topology. Instead of having a rectangular grid, I tried the D4 8x6 grids of hexabins. Okay, so here is a hexa here. Okay, for topology. Let's run the result. Okay. This is an hexabin lineup, right? So we have horizontally 8 grid points, right, and vertically 6. I get 6 layers from that, okay? And again, these are star symbol representation. So actually, this is only like, what should I say? This is more enhanced version of class package, okay? And well, for that, of course, it has this package has more other capability, okay? It allows you to put other measurements, okay? For example, we can the first one we put was a corpus, okay? The second one will be this one, the mapping, okay, of this result. I guess we are more interested in this, okay? Okay, because basically try to, where was that? Wine classes. Originally there are 3 classes. I guess that this is probably their favorite example because this does a very good job. If you in terms of if you use this as a classification, it looks like very good, right? Isn't it? Okay. You can see that here, this first class cluster around here, right? Okay. And now here, this is nicely clustered around here. There's only quite a few misclassified. If you try to divide, for example, if you try to divide from here as 1, okay, probably right here, you only have quite a few misclassified items. This result. The classes plus 1 basically just change that to red, green, blue. Otherwise, it would be red and green. Okay, so. And CH or changes, you can free spell that changes. Okay. You can use the first few characters to sort of uniquely identify type. Basically, that argument is called type of class you want to produce. Okay. And the changes part this. Okay. This is actually showing the training progress. Okay. So the mean distance across this unit was calculated at each step and down to 100 of iterations. So that R length will be the number of iterations, right? Okay. Training from alpha from 0.05 down to 0.01. You can see that. Okay. So finally, sort of stabilized with very short mean distance. Okay. Looks like training was successful. Look at this result. Okay. And basically, this part of counts is only just numbers of objects that located within each of these grid points. Okay. So, can you see? Can you see there are 3 clusters here? Lighter colors that means more counts, right? Isn't it? These 2 means that there's nothing there. Okay, there will be no object will be located within that. Okay, this gray color represent 0 objects located within that. Well, otherwise, we probably will cluster this together, right, isn't it? Okay? Because here we have majority line here. Here there's another cluster. It's probably a natural cluster from there, right? Okay. You look at the counts, but this is counts part. Okay? Yeah, I really like to see a counts part superimposed with this object particle within that. That would be nice to see the classification. Okay? And here, this is the mean distance to neighbor. Okay, this is plotting of that. Okay. So you can see that this grid point is more isolated because it says grade is average distance to neighbors, right? Okay. So originally we say we want to form one cluster here. Looks okay because here they are red color means they are shorter distance. Okay. So it could be more natural big cluster as well. And here this is another one showing the probably. So this is look at the individual variable level. Can you tell that from this that you can you see a natural cluster from this result? Not so easy, right? I think some of these graphics are really nice, some not really helpful. Okay? And finally, the last one about the quality, okay, or distance. But again, here because there are no object within these two grid points, so they are not shown here. Okay?
Will you have this posted on the site, the
Yeah, I will put this on that.
today? Or
Yeah, I'll put it on today. I guess I recommend you to read this one because this is only meant to be just introduction and read this covenant package. That. I'm not supposed to post this online. Right? I can find the links. I'll post a link directly so you can go it. Otherwise, in your remember last time I mentioned about this implementation. Of course, in my case, I have to put in the private library in my documents area. If you're a system administrator, then you should have just go to the program files and look at that. Okay. What was this column package? It should be located within the column package in the library column package and under doc. This is the menu there. Okay. Probably this is also a variable. I think it must be there somewhere. Okay. If I can find a link, I'll show you. Otherwise, you install column anyway, and you'll be able to see. Look at this package. Okay. Well, as they said, it's already a stable package, but they're still trying to come up with a newer algorithm to improve this package even more. Okay. I'm not sure we can finish everything here. Currently, I put something up. I put this slides about association rules. Okay. And I also put the slides about the text mining, but this is only a brief introduction about that. We have how many lectures left? Three, right? Hopefully we have enough time to cover that. Okay. At least to get some very basic concepts about these different topics. Okay, I'm going to start at this point for today. Do you have a question about the final project? And you're good with that?
Not yet.
Not starting, not yet. How about case starting?
Thursday.
So there will be no presentation for final project. I guess we cannot. We are restricted to the time that we have. Okay.